Good afternoon, guys. It's Dr. Edwards. What I'm going to do here now is to go through part of this homework problem, your second homework assignment, that is example 2.17 modified. And so what I want you to do here is to do all of the portions. You normalize the given wave function. You find B, the expectation value of X, the expectation value of X squared, and delta X, which is delta X is equal to the square root of the square of expectation value minus the, delta X is equal to the square root of the expectation value of X squared minus the square of the expectation value of X. And a similar expression is going to occur for delta p sub X. Part C that I've added here, you also ought to find the expectation value of Px, find the expectation value of Px squared, and find delta Px, which is the square root of the expectation value of Px squared minus the square of the expectation value of Px. Okay, so the first part has already been done for you, but every student must know how to implement this task in this course. So what you're going to do is we want to integrate psi star psi times dx, and we want to set it equal to 1. That's a requirement. If you set it equal to 1, you will get a specific value for capital A, a necessary condition. That's the feature that we call normalizing a wave function. So what does it mean when you say that the integral over a given space of psi star times dx equals 1? That means that's 100%. 1 is equal to 100%. So it's 100% chance that the particle is in that region of space. All right. So the region of space here is from x equals 0 to x greater than 0 and x less than a. So the particle is in that region, and we happen to already know the wave function. So this is a skill building problem. If you give, so somehow somebody has solved the Schrödinger equation, has gotten this value of the wave function. And if that's the case, what are the statistical values that you can find out about the wave function? That's what I want you to understand and to work with in this problem. So the first task then, after you normalize the wave function, so you put it here, and you effectively, in this case, square the wave function, because psi star psi is all real here. There's no unit I, so there's no difference between psi star and psi. You put it in there, you use the for rule, as you remember, and you square the quantity here. Now all of that is the integrand, where lowercase a is a constant, capital A is a constant, but you just don't know the value of capital A right now. Now when you integrate term by term, the integral of a sum is the sum of the integrals. So you get then capital A squared comes out, times the quantity lowercase a squared x cubed over 3 minus a x fourth over 2 plus x5 over 5, integrated between, evaluated between 0 and lowercase a. So when you put in the upper limit, you get this result. You put in the lower limit, you get 0. So the author doesn't even write it. So as I say, then once you substitute everything, you get the least common denominator here, which is 30, and add term by term. And what he didn't show you is that he set this equal to 0. And when he set that equal to 0, he's able to solve for, he set this equal to 1. And then he's able to solve for capital A as the square root of 30 divided by lowercase a to the fifth. Let me go on. So now this is the task, and I want you to go through that. Find the expectation value of x. So what he done here, I don't like the way he done this. You need to put x in between psi star and psi. So let me see. That's what I want you to do. And I'll show you that when I do the evaluation for the expectation value of px. But in this case, it doesn't matter. It's the same results. So effectively, he squares a squared, put it there, multiply, does the for rule again, and then multiply it by x, and he gets this term. He substitute term by term and evaluate, and he gets the value of lowercase a over 2. So that means then the expectation value says that it's very likely that the particle is halfway all the time, most of the time, is halfway between x and x equals a and x equals 0. That makes sense. It's more likely to be midway. So here you're getting the understanding that we don't know exactly where the particle is, but we know though that it is somewhere in this region. So while we can't say exactly where it is, we can calculate these statistical values. All right, I've gone on here and I've calculated the expectation value of x squared. Let me do this. All right, the expectation value of x squared. Notice how I do this here. So this is a star, and I put x squared sandwich in between, and this is a, and now I multiply x squared times what's to its right. I multiply x squared times this, and I get ax cubed, and I also get x to the 4th. I factor out the value of a capital A squared, 30 over lowercase a to the 5th. Now use the for rule once again. Let me bring this over here. So that's what you get. Then I use the for rule once again, right here. And now this is the term to be integrated. And I integrate that term there, on, and then evaluated it from 0 to lowercase a. And when I evaluate it from 0 to lowercase a, it turns out that the expectation value of x squared is 2/7 a squared. Well, x has units of meters, lowercase a has units of meters, so the units are fine here. Is 2/7 of a squared. And as I said, the uncertainty in delta x then is the square root of the uncertainty in x squared minus the square of the uncertainty in x. And so I substitute the two values I've gotten. I get the uncertainty in x there. Now I want you to also calculate the uncertainty in px, and that's going to turn out to 0. But what I want to really show you now is how to find the uncertainty in px squared. All right. So you have to integrate the expression from 0 to a of psi star. And px squared then is negative h bar squared d second dx second. So you have to put that in between psi star and psi. And then you have to differentiate this, what follows d second dx twice. You have to differentiate twice because this is a second derivative. And then multiply that by psi star before you proceed to make the calculation of the expectation value of a piece of x squared. All right, so here we go. So you can factor out what did we factor out? X bar squared, 30 over a to the fifth. All right, so we have that. We leave this term just as it is. And notice that it's been differentiated once. When you differentiate ax minus x squared, you get a for just the first term, and you get a negative 2x for the second term. All right? Now you have to differentiate this one more time. And when you differentiate this, you get just a negative 2. All right? There was a negative here, so there should have been a negative. A negative times a negative becomes a positive. So you get then 60 over a to the fifth h bar squared. Now the integral to be done is from 0 to a of a x minus x squared dx. Because you only pick up a negative 2 over there in the set. Now you proceed to perform this integration. You go on, you take, and you evaluate it at the upper limit minus the lower limit. And because it's 0 at the lower limit in this problem, but in some problems, it is not 0. So you have to be real careful. And now you find the uncertainty, you find the expectation value of px squared as being 10 h bar squared over a squared. And then you can find the uncertainty in px, as I said, which is this number here. All right, that's what so I'm going to stop right there, let you go on now and finish this problem and turn this in to me, okay? Play this video as many times as you wish in order to understand for a continuously given wave function, psi in this case. This is skill buildings. If you're given the wave function, you should be able to find the statistical quantities associated with that wave function. Once again, you always have to normalize it if it's not normalized. And in this case, it's not normalized. So, but the way you normalize it is the inner product then of psi with psi star. Integrate that from 0 to the upper limit and set all that equal to 1. You can find what it takes to normalize the wave function. And then you can solve it. So I want you to complete this homework assignment and turn it in to me. Feel free to contact me. You should check your emails daily and see if there are additional messages from me. And you can contact me if you need to too. Have a good day.